In the name of Almighty God, I am Master Sankoshi, and today I want to talk about chemical reaction engineering capsule multiphysics simulation software, the dispersed two-phase flow with a species transport multiphysics interfaces. Dispersed two-phase flow with a species transport is a predefined multiphysics interface that coupled dispersed two-phase flow with mass transport in both the continuous phase and in the dispersed phase. Selecting laminar flow under the chemical species transport, then select dispersed two-phase flow with a species transport branch of the model wizard or at physics windows, a mixture model laminar flow interface along with a continuous phase transfer of diluted species interface and a dispersed phase transfer of diluted species interface are added to the model builder. In addition, the multiphysics node is added including the multiphysics coupling feature, dispersed two-phase fluid diluted species. The dispersed two-phase fluid diluted species feature predefines and controls the coupling between the separate interfaces in order to facilitate easier step and setup of the models. In this section, we want to go through the dispersed two-phase laminar flow with the species transfer interface, the dispersed two-phase flow diluted species coupling features, physics interface features, the continuous phase transfer of diluted species interface, the dispersed phase transfer of diluted species interface, the dispersed two-phase laminar flow with the species transfer interface. The multiphysics interface is used to simulate two-phase flow in the laminar regime, coupled to a transfer of diluted solutes in each the two fluid phases. It combines the mixture model laminar fluid, the continuous phase transfer of diluted species interface, and the interspersed phase transfer of diluted species interface. The dispersed two-phase fluid diluted species multiphysics coupling, which is added automatically couples the two-phase fluid with mass transport. The mass transport interfaces solve for the development of one or several solutes present in the continuous and dispersed fluid phase. The interface can be used for stationary and time-dependent analysis in two-dimension axis symmetry, and also for three dimensions. On the constituent physics interfaces, the first type, the mixture model laminar flow interface, solves one set of Navier-Stokes equations for the momentum of the mixture. The pressure distribution is calculated from a mixture average continuity equation, and the velocity of the dispersed phase is described by a slip model. The volume fraction of the dispersed phase is tracked by solving a transport equation for the volume fraction. The continuous phase transfer of dialysis species interface solves for an arbitrary number of solute concentrations present in the continuous phase. The species continuous include transport by convection and diffusion between the phase, as well as reactions and solute extraction between the continuous and dispersed phase. The dispersed phase transfer of diluted species interface solves for an arbitrary number of solute concentrations present in the dispersed phase. The species equations include transport by convection and diffusion between the phase, as well as reaction and solute extraction between the continuous and dispersed phase. Now I want to go through the dispersed two-phase fluid diluted species coupling feature. The dispersed two-phase fluid diluted species multiphysics coupling is used to simulate the fluid flow of a liquid containing a dispersed phase together with mass transfer occurring in the continuous phase and dispersed phase. The coupling feature also supports mass transfer, solute extraction between the phases. Now I want to go through the domain level synchronization. The dispersed two-phase fluid diluted species coupling synchronizes the features in a mixture model interface with those in the transport interfaces for each of the phases: continuous phase transfer of diluted species and dispersed phase transfer of diluted species. When added, the velocity field and the volume fraction of each of the phases computed by the mixture model interface is synchronized to the species transport interface for each phase. Now I want to go through the solute extraction. Extraction is the process where a species transferred between two immiscible phases due to different relative solubilities in each phase. Physically, this transfer process occurs at the phase separating interfaces, the bubble or the droplet surfaces in the case of dispersed two-phase fluid. Use the checkboxes to select which of the species that can be dissolved in both phases and is subjected to extraction. When multiple species are present in each phase. The species in the two mass transport interfaces are paired by position from top to bottom in the concentrations released in the dependent variables section when selecting an interface. During selection, the species in the continuous phase physics interface is transferred into or from the corresponding species in the dispersed phase physics interface. The rate at which a species is removed from the continuous phase, we want to go through the equation 3-21. RASC is equal to minus km multiplied by copy CC minus CD multiplied by alpha S is equal to minus RAD, where CC and CD are the concentration in the continuous and the dispersed phase respectively. Kp is the partition coefficient determining the phase partitioning at equilibrium. Alpha S is dispersed phase specific surface area, square meter per cubic meter, and km is a mass transfer coefficient governing the transfer from the bubble or droplet surface to the bulk of each phase. Note some same source term but with opposite sign is added for the corresponding species in the dispersed phase. Assuming that the dispersed phase particles are spherical, a specific surface area is computed from the dispersed phase volume fraction phi d, and the particle reduce RP in a manner of the alpha S is equal to 3 multiplied by phi d divided by RP when modeling phase transfer with a net mass change between the phases and the corresponding change in the particle radius. Solve for interfacial area can be enabled in the settings of the Coop mixture model interface. In this case, the resulting specific area is used in the extraction rate. Now I want to go through the settings. The label is a default multiphysics coupling feature name. The name is used primarily as a scope prefix for variables defined by the coupling node. Refer to such variables in expressions using the pattern name.variable name. In order to distinguish between variables belonging to different coupling nodes or physics interfaces, the name string must be unique. Only letters, numbers, and underscores are permitted in the name field. The first character must be a letter. The default name for the first multiphysics coupling feature in the model is DDS1. The main selection, the dispersed two-phase fluid diluted species coupling, is automatically defined on the intersection of the selections for the coupled interfaces. The selection list displays the domain where the coupling feature is active. Now I want to go through the coupled interfaces. This section defines the physics involved in the multiphysics coupling. The list dispersed two-phase fluid, continuous phase species, and dispersed phase species include the applicable physics interfaces of each kind. The default values depend on how this coupling node is created. If it is added from the physics ribbon for Windows users, or physics contextual toolbar for Macintosh operating system and Linux users, or context menu for all users, then the first physics interface of each type in the component is selected as the default. If it is added automatically when a multi-physics interface is chosen in the model wizard or at physics window, then the two participating physics interfaces are selected. You can also select none from either list to uncouple the node from a physics interface. If the physics interface is removed from the model wheeler, for example, mixture model laminar flow is deleted, then the dispersed two-phase flow list defaults to none as there is nothing to couple. To click the Go to Source button to move to the main physics interface node for the selected physics interfaces. If a physics transfer interface is deleted and then added to the model again, then in order to re-establish the coupling you need to choose the physics interface again using the list in the coupled interface section. This is applicable to all multiphysics coupling nodes that would normally default to the core 1% interface. See multiphysics modeling workflow in the Capsule Multiphysics reference manual. Turbulence section. When the fluid flow interface uses a turbulence model, select an option from the mass transport turbulence model list. Case Crawford high Schmidt number or user-defined turbulent Schmidt number. For user-defined turbulent Schmidt number, enter a turbulent Schmidt number SCT dimensionless. The turbulent mass transfer added to the concentration equation is defined as JTI is equal to minus micro T divided by Schmidt number multiplied by delta Ci, where U microity is the turbulent viscosity defined by the fluid interface and turbulent Schmidt number as the CAT depends on the mass transport turbulent model used. Now I want to go through the physics interface features. Physics nodes are available from the physics ribbon toolbar. Windows users, physics context menu for Macintosh or operating system or Linux user, or right click to access the context menu for all users. In general, to add a node, go to the physics toolbar no matter what operating system you are using. Now I want to go through the mixture model laminar flow. The available physics features for the mixture model laminar flow interface are listed in the section domain and boundary nodes for the mixture model interfaces in the CFD module users guide. Now I want to go through the continuous phase transfer of dilated species and dispersed phase transfer of dilated species. These interfaces are versions of the transfer of digital species interface. The interfaces extends the functionality by supporting phase-specific mass transfer, pores, media transfer, and migration in an electric field, are however not supported in the interfaces for phase-specific mass transfer. Apart from transfer properties, the available features are described in this section: domain, boundary, and pair nodes for the transfer of digital species interface. Now I want to go through the continuous phase transfer of diluted species interface. The continuous phase transfer of diluted species interface is used to calculate the concentration of one or several diluted solids present in a continuous phase in a fluid with multiple immiscible phases. Transfer and reactions of the species within the continuous phase can be handled with this interface. The driving forces for transfer can be convection by the continuous phase, velocity diffusion by fixed law, and turbulent diffusion. When interface is used in the dispersed two-phase flow diluted species coupling feature, the interface supports simulation of transfer of one dimension, two dimension, and three dimension, as well as for axisymmetric component in one dimension and two dimension. The dependent variable is the molar concentration C. Modeling multiple species transfer is possible, whereby the physics interface solves for the molar concentration CI, which is species I. It should be noted that the concentration solved for is the total concentration Ci is equal to phi C Ci, comprised of the phase volume fraction phi C and the continuous phase concentration CCI. For each concentration solved for, the interface defines a variable TDS dot phase, the underlying concentration corresponding to the phase concentration CSCI. This can be used in boundary conditions and reaction rate expression when the phase concentration is to be prescribed or used. The continuous phase transfer of diluted species interface is a version of the transfer of diluted species interface, except for the transfer mechanism. Settings described below in the interface settings are identical to those available in the transfer of diluted species interface. Now I want to go to the transfer of mechanisms. Mass transfer due to diffusion is always included. Use the checkboxes available under additional transfer mechanisms to control other transfer mechanisms. By default, the convection checkbox is selected. Clear the checkbox to display and disable convective transfer. Phase-specific transfer is enabled by default. When enabled, the phase type can be set to continuous or dispersed. Clear the phase-specific transfer checkbox is disabled to the support for a volume fraction and phase-specific transfer. Now I want to go through the dispersed phase transfer of diluted species interface. The dispersed phase transfer of diluted species interface is used to calculate the concentration of one or several diluted species solutes present in a dispersed phase in a fluid with a multiple immiscible phases. Transfer and reactions of the species within the continuous phase can be handled with this interface. The driving forces for transfer can be convection by the dispersed phase, velocity diffusion by fixed law, and turbulent diffusion when the interface is using the dispersed two-phase fluid diluted species coupling feature. The interface supports simulation of species transfer in one dimension, two dimension, and three dimension, as well as for axisymmetric component in one dimension and two dimension. The dependent variable is the molar concentration. C. Modeling multiple species transport is possible, whereby the physics interface solves for the molar concentration CI of each species I. It should be noted that the concentration solved for is the total concentration CI is equal to phi d CADI, comprised of the phase volume fraction phi d and the dispersed phase concentration CADI. For each concentration solved for, the interface defines a variable TDS.FS underlying concentration corresponding to the phase concentration CADI. This can be used in boundary conditions and reaction rate expressions when the phase concentration is to be prescribed or used. The dispersed phase transfer of duality species interface is a version of the transfer of duality species interfaces, except for the transfer mechanism settings described below. The interface settings are identical to those available in the transfer of duality species interfaces. Transfer mechanism must transfer due to the diffusion is always included usage checkbox available under the additional transfer mechanism to control other transfer mechanism. By default, the convection checkbox is selected clear. The checkbox to disable convective transfer phase specific transfer is enabled by default. When enabled, the phase type can be set to continuously disperse. Clear the specific transport checkbox to disable the support for a volume fraction and phase-specific transport. Transport properties use this node to define the volume fraction, the convective velocity, and diffusion coefficient to use the phase-specific transfer in continuous phase transfer of duality species interface or a dispersed phase transfer of duality species interface. Conservation of mass of a species are in an immiscible fluid phase is formulated as follows. The derivative phi rho I based on the time plus delta phi rho I u is equal to delta brackets di delta phi rho I bracket plus RMI, where phi is the phase volume fraction, rho I is the species density, and u is the mass average velocity of the phase. Dr is the diffusion coefficient, and RMI is the species mass source. Using the species density definition, rho I is equal to CAPI where CAPI is the species phase concentration, and diving by the molar mass MI, the conservation equation becomes the derivatives phi CAPI based on the time plus delta phi CAPI u is equal to delta di delta phi CAPI plus Ri. Choosing to solve for the total concentration Ci is equal to phi CPI, the equation is derivative of Ci based on the time plus delta CIu is equal to delta di delta Ci plus Ri. The following equations are solved for the total species concentration in the continuous and dispersed phase respectively as follows. Here, DTR is a turbulent dispersion coefficient accounting for the enhanced transport in turbulent fluid. It is added by dispersed two-phase and the diluted species coupling feature when the mixture model interface is using a turbulent model. Thank you so much for watching my tutorial video until the end. Today is 18th of May 2026. Time is 10:03 a.m. You can download the related simulation file from github.com/masterscript.